Hey, 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 what's happening, Webster Groves? This is 8th grade science, wave energy, goal 4 video notes. And in this goal, students will be understanding how the properties of a medium affect the speed of sound. If you're going above and beyond that goal, you're able to look at a situation and predict how the properties of that situation are going to affect the speed of sound. So here we go. A bit of a review before we get started. Sound. What is sound? Well, at this point we should know what sound is. If not, you wrote it down in your goal 2 notes. So just a quick review, a quick summary. Sound is a disturbance that travels through a medium as a mechanical wave with a longitudinal wave movement. How does a sound wave begin? It begins as a vibration. You have to have that initial vibration as the disturbance so that the wave can travel. What mediums can sound travel through? It can travel through all types of mediums. They just have to be made of matter. So any solid, any liquid, any gas. These are the things we have to understand in order to catch up to the speed of sound. You like that? Catch up? That one's free. Okay, so what does the speed of sound depend on? Well, it depends on three things. The speed of sound depends on the elasticity, density, and temperature of the medium the sound travels through. Okay? The main one being the elasticity. Okay, so if we look at these charts, we can see that air at 0 degrees Celsius only moves about 331 meters per second. That's still pretty fast. Meters per second, okay? And then air at 20 degrees Celsius moves faster than that. This is kind of normal room temperature, 343 meters per second. Liquids, on the other hand, move sound even faster. In fresh water, moving 1,509 meters per second, and in salt water, moving even faster than that. You can begin to see the role that elasticity is playing here. Solids. Solids make sound move the fastest. So you can see as the elasticity in the solids change, you can see that the speed of sound changes. Glass being the fastest with 5,170 meters per second. Okay, imagine how fast that is in 1 second. Over here we have a bar graph, and this bar graph kind of shows us the difference between gases, liquids, and solids by giving us some examples and really showing us that gases move sound the slowest, liquids in the middle, and solids move sound the fastest. Okay, so sound moves through these mediums in this way because of the elasticity, the density, and the temperature. So let's talk about those three things. Okay, what is elasticity? Definitely new word for most of us. Elasticity is the ability of a material to bounce back after being disturbed. Okay, so think of a rubber band versus a chunk of clay. Okay, you stretch out this rubber band, it's going to go back together. Okay, it's going to bounce back after it's being disturbed. On the other hand, you stretch out this clay and it's not going to really bounce back. It's not very elastic. So rubber band, very high elasticity, clay, not. So the way this works, the more elastic a medium, the faster sound travels in it. Sounds can travel well in solids, which are usually more elastic than liquids or gases. The particles of a solid do not move very far, so they bounce back and forth quickly as the compressions and refractions of the sound waves pass by. Most liquids are not very elastic. Sound does not travel as well in liquids as it does in solids. Gases generally are not very elastic. Sound travels slowly in gases. So think about it this way, okay? A bouncy ball. You throw a bouncy ball onto the floor. The material of that bouncy ball is going to compress and rarefact. It's going to compress and rarefact very quickly. On the other hand, okay, if you throw a rock into a pond, that water is not going to bounce back and forth as quickly as that bouncy ball would have. Okay? And if you move something through the air, those air particles are not going to move back in place very quickly. So it's all about the elasticity of these states of matter that allow sound to move in the way that they do through them. Okay? How does density affect the speed of sound? Again, density, how much matter there is in a given amount of space or volume. Okay, so we can see that this, probably can't see the yellow very well, but this square is more dense than this square. Okay, same volume, more matter, less matter. Okay, the denser the medium is, the more mass it has in a given volume. In a material in the same state of matter, sound travels more slowly through denser mediums. Okay, but they have to be in the same state of matter. Okay, so the denser a medium is in a solid, it is going to move more slowly. So, for example, so sound travels through a dense metal such as lead or silver more slowly than in iron or steel. Okay. The particles don't move as quickly as in those of a less dense material. It's almost like they're just crowded together and they can't really move back. They're not very elastic because they're so packed together they can't move back and forth very quickly. Okay, so that's density. Temperature. In a given medium, sound travels more slowly at a lower temperature than at a higher temperature. So lower temperatures moving slowly, higher temperatures moving fast. What we know, going back to the kinetic molecular theory, what we know is that the particles in warm matter are already moving quickly. Okay, so for them to be very quickly elastic and move their particles back and forth doesn't take much. They're already warm. At a low temperature, the particles of a medium move more slowly than at a high temperature. So they are more difficult to move and return to their position more slowly. Okay, so temperature, sound travels slowly at lower temperatures, higher than at higher temperatures. Okay. All right. Our goal was to understand how the properties of a medium affect the speed of sound. Okay. And those three properties we talked about were elasticity, density, and temperature. Okay. So those are the properties you're going to need to know how those affect the speed of sound. We're going to wrap this up by listening to a professor at UCLA speak on the same topic. Here we go.
Since sound is a wave, it travels at a definite speed. But the speed of the wave depends on what it's traveling in, the medium. Imagine a race. 3 speakers emit a beep all at the same time. Beep, beep, beep. Time equals 0. Which beep is going to win the race? Beep. In air, the speed of sound is 340 travels much slower, 340 meters per second. That's about 1 mile per 5 seconds. So if you count the amount of seconds between the light and the sound, you can accurately predict the distance to the lightning strike. Every 5 seconds you count, 1 mile of distance.
Alright, well that's it, that's all. Bring your questions to class, and we'll see you later.